All right, I want to welcome a fellow North Carolinian. We were on the plane together. Josh Starmer is our keynote. We're so excited to have his not just knowledge, but his musical gifts with us this morning. So I'd like to welcome Josh Starmer to the stage.
Hey! Can you hold the mic for me?
Yes, I am.
I have a silly song for you. I should have brought my tuner. PyData in Seattle. Oop, we're going to start this over. PyData in Seattle and Bellevue. I'm glad to be here 'cause I get to meet you. Hooray! Hooray! Hello, I'm Josh Starmer, and welcome to PyData Seattle in Bellevue. So, without further ado, I'm going to talk about communicating concepts, and hopefully it'll be clearly explained. And now, I know that this talk is titled Communicating Concepts Clearly Explained, but we're actually going to start with another talk called 3 Tips to a Long, Successful, and Fun Career, or Why I Don't Worry About AI Taking My Job and Sense of Purpose Away From Me. And that might be a pretty strong statement. I worry a little bit about it, but maybe not as much as other people. And I'm going to give you 3 tips as why I don't worry as much, maybe. Number 1 is try to be a good helper, and we're going to talk about what that means in just a second. Number 2 is be curious, and we'll talk about that in a little bit. And number 3 is try to clearly communicate, or communicate clearly. So I'm going to give you a few examples of how these things have helped me have a long and successful and fun career. So back in the day, my grandfather, he repaired elevators for a living. And there he is in the elevator. And on weekends, my pop used to help him. And my pop was a good helper because every time his pop, my grandfather, needed a tool, my pop had one waiting for him. Bam. Being a good helper means knowing what needs to be done before it needs to be done, and being ready for it when it happens. Now, I don't have to be fixing an elevator to be a good helper. I can always at least try to be a good helper. All I have to do is look around and have a little curiosity. When I'm curious and ask questions and observe, I can learn what needs to get done. And this is, the story of my whole life is a function of me wandering around and going, what needs to get done? And I look around and I see things that need to get done, and all that has done is open doors for me. Anyways, once I learn what needs to get done, I can be a good helper and do it. In my various jobs, one skill that has always made me essential and got me promotions was I always tried to be a good helper. For example, whenever I had downtime at work, I went around to learn about what everyone else was doing, and then I would try to find a way to help them. This is what led me to make StatQuest to begin with. I used to work in a genetics lab, and all these people were generating all this data, and they didn't know what to do with it. And so I stepped in and I helped them out. I did some real basic statistics for them, and then I thought, well, I shouldn't just do the statistics. I should teach them what it means. You know, because there's some, I don't know how familiar you guys are with statistics, but there's a concept called a p-value, which is sort of backwards from what you think it is. And so I spent a lot of time trying to help my coworkers understand these basic statistic concepts. And as a result, well, I got ahead of myself. Anyways, my coworkers were completely baffled by statistics, but they needed to understand it because their jobs depended on it. So I tried to come up with a way to explain it to them. And in order to explain statistics to them, I had to use examples they could relate to. So instead of using abstract objects like marbles and urns to explain statistics concepts, which is what every single statistics class I took used, I used mice and genes since my coworkers were all mouse geneticists. And because my coworkers hated math, I think they took a math class in college and they're like, no, I'm going to do genetics instead. I always try to teach using a visual approach rather than one that relied too heavily on equations. Note, I did not know that doing this would lead to a successful YouTube channel. This is just fortune. But later on, we'll talk about some reasons why this worked out so well for YouTube. Anyway, if you don't know, by the way, I know a lot of people do, but if you don't know, I have a YouTube channel called StatQuest with Josh Starmer. That people watch. Anyway, all I wanted to do was help out my coworkers. Because I could clearly explain what I was doing. Get this, they trusted me with their data. And because they trusted me, they wanted me to work on their most important projects. So even though I was just sort of like a helping hand, I got on these fancy, I don't know if you're familiar with it in the world of biology, but when you get a paper in manuscript, that's, a paper in Nature, that's kind of the equivalent of like having a #1 hit on the radio. And I got a bunch of those. I got to be on a bunch of those, which is amazing, right? So I've gotten to be on a bunch of #1 hits. Anyways, I became the statistician that everybody wanted to hire. And if I wanted to, I probably could have had a lot of fun working with these people for the rest of my career because they were awesome and doing cool things. So bam. So this example illustrates the 3 tips I mentioned for a long, successful, and fun career at the start. It illustrates me trying to be a good helper by finding out what needed to get done and doing it before anybody asked me to do it. Nobody said, I need you to help all these people with statistics. I just poked around and I was like, oh, that's what they need. Number 2, I was curious because I was just interested in what they were doing. They're all sitting there at this laboratory bench pipetting things and doing all kinds of crazy stuff. And I was like, oh, tell me about it. This looks interesting. And number 3 is me trying as hard as I could to communicate clearly. And I still have a lot to go, but man, I was really bad back then. It was really hard work, but I succeeded anyways. And to be clear, good communication isn't just for making YouTube videos. It's about how you establish trust. When people trust you, they will want you on their team, and they'll be willing to share their most important work with you. So I think it's like a super important skill, and it's not just something that I say because I've got a YouTube channel. I think it's really important for everybody. Anyways, so I'll give that a big bam. Okay, now let's see how these 3 things work in a StatQuest video. Specifically, we're going to talk about how I turned this equation into my YouTube video, PCA Step-by-Step. This video has been viewed over 3,400,000 times. And it has over 67,000 likes or thumbs up. And I think the ratio of thumbs up to thumbs down, it's like, I think I'm like 99.4% thumbs up. So there's occasional people that look at this and they go, ugh, I hate it. But almost everyone loves it. Okay, in summary, I believe it's safe to say that a lot of people have watched and liked and learned from this video. So now let's talk about how I turned this equation into a successful YouTube video. First, instead of starting with this equation, the video starts out with a simple data set. The data set has rows of gene expression data for 2 genes in 6 different mice. I chose this data set because at the time I was working in a mouse genetics lab that studied mice. And my coworkers were the primary audience that I had in mind. And at the time, PCA plots were starting to show up in journal articles about mice, and I wanted to prepare my coworkers for them. By the way, I didn't know what PCA was either. I had to figure it out. I just saw them in journal articles. I was like, oh, I keep seeing these graphs. What the heck are they? And I need to learn this stuff, and then I'm going to teach it to all my coworkers because they're going to need to know it too. So it's not like I knew what this PCA thing was and just decided to teach people. I looked at it and went, I have no idea what that is. It looks scary, but I got to figure it out because these people have to know. Okay, so anyways, I was trying to be a good helper in this case. That being said, by trying to be a good helper with my coworkers, I stumbled over one of the most important things in clearly communicating anything. And that is to know your audience, know who you're talking to. Knowing your audience helps guide every decision you make when you try to communicate something. For example, if I'm going to teach someone how to drive, and they know how to ride a bike, then I'll explain how to drive in terms of how to ride a bike. The handlebar is the steering wheel, and the pedals are the gas, etc. In contrast, if they knew how to ride a horse, then I'd try to explain how to drive in terms of how to ride a horse. Giddy up. And if someone had piloted a boat before, then I would explain how to drive in terms of how to pilot a boat. Anchors away. Anyway, in this case, I was making a video specifically for my coworkers who all did genetics with mice. So I used an example based on genes and mice. Boop, boop. However, on the off chance that someone other than a mouse geneticist might be interested in learning about PCA, I talked about how instead of mouse data, we could have rows of test scores and columns of high school students. Or we could have rows of business metrics like market capitalization and the number of employees and columns of businesses. The reason I gave specific examples of data sets for genetics, teaching, and economics instead of only using abstract terms like variables and samples is that it makes it easier for people to imagine how PCA could be applied in a variety of situations. And, at least for geneticists, teachers, and business folk, easier to imagine exactly how they might use PCA. So instead of having to imagine how they might use PCA, they get to see it firsthand, and then they go, oh, I get it. So this is an example of me trying to clearly communicate to a wide variety of people. That said, I also mentioned that you could think of the rows as variables and the columns as samples. So the point so far in the video is that we have some data. And that data can come from a wide variety of people with different backgrounds and expertise. Then I switch things up by shrinking the data set to just one row. Hey, look, it's Stat Squash. If you don't know, this furry thing in the corner is called Stat Squatch, and sometimes we just call him Squatch.
Hey, Josh, why didn't you just start out with a single row of data?
Good question, Squatch. Because starting out with 2 or more rows helps people imagine a lot of data better than a single row.
Okay.
Anyway, given that we have 1 row of mouse gene expression data, I can show how we can plot that data on a number line. Even though a number line graph is simple, it can still be useful for showing that there are 2 groups of mice. These 3 mice form one group on the number line, and these 3 mice form another group. Now that we know we have 2 different groups of mice, we can make testable hypotheses about why they form different groups. Or if we already knew that we had 2 types of mice, the graph confirms that we did the experiment correctly. So looking at the data in the form of a graph can be super helpful and is, generally speaking, the first step in any data analysis. I then show that we have gene expression data from 2 different genes, or 2 rows of data. Then we can plot the data on a 2-dimensional graph. That also shows how the mice can be easily separated into 2 groups. Then I show that if we add gene expression values for a 3rd gene, giving us 3 rows of data, then we can sort of draw a 3-dimensional graph of the data that helps us identify the clusters of mice. But this 3-dimensional graph is kind of clunky on our 2-dimensional screen, right? If we had our hollow deck or some sort of fancy thing, maybe we could get away with it. But it's awkward on a flat screen. I just said that. And if we add gene expression values for a 4th gene so that we have 4 rows of data, then we can no longer graph the data. And I know what some of you guys are thinking. You're like, well, we could use different colors or shapes and things like that. Yes, you can sneak in some extra dimensions. But sooner or later, you're going to hit a wall where you can no longer display the graph of all the data. And that means we can't see if the mice form clusters and how many mice are in each cluster. So we can't see these things anymore. And that gives us a big wah wah. So we have a problem. When we have 4 or more rows of data, then we can't draw a graph of the data and identify clusters. However, knowing that we have a problem is a great thing.
Hey Josh, why is it so great to know we have a problem?
Good question, Squatch. Knowing we have a problem is a great thing because people love to learn how problems can be solved. Think of any movie you've seen or novel that you've read. Boop, 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 boop. They all start out by introducing a problem. For example, in the hit movie Troll 2, we have a bunch of people being threatened by goblins.
How will they survive?
Keep watching and you'll find out. Or take any superhero movie, and in the first part you'll learn that the entire universe is being threatened by some evil dude.
How will we survive?
Keep watching and you'll find out. Or take the rom-com movie, or any rom-com movie for that matter, like Marry Me, starring Jennifer Lopez and Owen Wilson. How will they deal with the fact that they just got married before knowing each other?
I'm dying to know.
Really?
Yeah.
Squatch loves a good rom-com. Not many people know that, but when we're on the plane, that's all Squatch does. Just sits next to me and watches rom-coms. Okay. Anyway, people in Stat Squatch love to learn about problems, and they love to see them get solved. Note, most scientific manuscripts, or presentations for that matter, also start by stating a problem. However, they tend to be boring as all get out because they usually assume that the reader or the watcher already appreciates the importance of that problem and why solving it might be useful. Don't make this mistake. Don't assume whoever you're talking to already appreciates the problem and knows why solving it would be helpful. In other words, if you want to create something that has broad appeal, you have to appeal to a broad audience. And one way to do that is to make sure you start with a thorough introduction that does not assume someone is already interested in the topic. Pretty much every book and movie that is not boring will spend a good chunk of time making sure that you understand the problem and that it needs to be solved. And that's why I spend the first third of a video just illustrating the problems we need to solve. Bam. So now we know we have a problem.
Graphs are useful for spotting things like clusters, but when we have more than 3 rows of data, it's hard to graph.
And now we have a way to, and now we have to figure out a way to solve it. And in this case, we can solve it with principal component analysis, called PCA. Bam. Note, so far we've talked about what an introduction should do. An introduction should introduce a problem that we're dying to see solved. Everything in the introduction should focus on that task. This means I avoided rambling about the history of PCA or the history of principal component analysis. Nobody cares about the history of PCA, at least not at this point in a video. Also, you might notice that I haven't mentioned any principal component analysis terminology like eigenvectors or eigenvalues or loading scores. These are important things, and we'll get to them, but they don't help introduce the problem, so we don't need them in the introduction. An introduction, all it needs to do, and it needs to do it, is introduce a problem that we're dying to see solved. Bam. Okay, now that we know and appreciate that there's a problem that needs to be solved, and we can solve it with PCA, aka principal component analysis, now we can start to teach how PCA works. However, I don't just want to talk about how PCA works. I also want to show them how it works. Showing instead of talking helps people get a deeper understanding of how things work, because it makes it much easier for people to get a mental picture of something if you start with an actual picture. So to do this, we go back to a data set with just 2 rows of data and use it to draw a graph. Then we center the data on the origin of the graph. Beep, boop, 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 boop. And then we draw a line through the origin. Note, this is just a random line. Other than going through the origin, there is nothing special about it. Then we just rotate the line until we minimize its distance from the data. And this line, the line that goes through the origin and minimizes its distance to the data, is the first principal component.
Bam.
No, not yet, Squatch. Remember, the purpose of this talk is not to teach PCA, but to talk about why this PCA video illustrates clear communication. The important point is that we were able to see the difference between lines that are not the first principal component, boop, 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 and the line that ultimately ended up being the first principal component. To repeat, we were able to see the difference in the lines. And even though we had the math on the screen, we didn't fixate on it. We were mostly just interested in the animation. What we saw is that there are lines that don't really fit the data very well. And then there's the first principal component, which fits the data really well. And as a result, we have a better sense of what the first principal component represents.
Bam.
Bam. Okay, once we have shown people what the first principal component is, we can finally start to introduce some terminology. For example, we call this line principal component 1, or PC1 for short. And a unit vector in the same direction of PC1 is called an eigenvector. So at this point, we're learning all kinds of details about PCA. But we're missing something critical. Humor. You guys ready for a really bad, tasteless joke? Brace yourselves. Okay, so because this specific principal component goes out along gene 1, the gene 1 axis, 4 units. For every 1 unit that it goes up the axis for gene 2, so we go over 4 and up 1, that's sort of the slope for this, this red dotted line. I compared this ratio to making a cocktail. And I said, because I thought it was funny, pour over ice and serve.
Ugh, that's the worst joke ever.
Regardless of whether or not people appreciate my bad joke, it helps them understand that gene 1 is 4 times more important to PC1 than gene 2. And that makes it a lot easier to understand how to interpret a principal component's loading scores. Loading scores just tell us how much of each original axis was used to create a principal component. And the fact that we have 4 times as much of gene 1 in PC1 than gene 2 tells us that gene 1's role in PC1 is 4 times as large. Bam. Okay, now that we understand how to find PC1 and we've learned a bunch of terminology, we can apply everything we just learned to finding PC2, principal component 2, given the fact that the new line has to be perpendicular to principal component 1. Once we figured out PC1 and PC2, which are perpendicular to each other, all we need to do is rotate everything so that PC1 is horizontal, and then we plot the data given the new axes. And we're done drawing a principal component analysis graph. Double bam. Now that we know how to create a principal component analysis plot using data from 2 different genes, so we start off with a very simple example. Now we're ready to do something a little more complicated. We can introduce a slightly more complicated example that has 3 rows of data. So this helps us understand how we can then generalize the concept to even more genes. We saw 2, and now we're going to see 3, and hopefully eventually we'll go, oh, I can imagine how it would work for 4 or 5 or 6 or 10,000. Anyways, when we have 3 rows of data, we have a 3-dimensional graph, 1 axis for each gene or variable that we measured. So now the idea is to show how we repeat the exact same steps we did before, only now we do them 3 times instead of 2. So the first thing we do is center the data around the origin. Then we find the best fitting straight line that goes through the origin, and we call that PC1. And the recipe for PC1, or the loading values that we just talked about, has 3 ingredients, 1 for each gene in the original data. And gene 3 has the most influence in the direction of PC1 is pointed. Now we find PC2 by drawing a straight line through the origin that is perpendicular to PC1 and rotating it in a plane that is perpendicular to PC1 until we find the best fit. This is a little weird for some people to understand. It's just the fact that in 3 dimensions, you can have something perpendicular and still have, how do I do this? I'm just going to yell at you. In 3 dimensions, the arm is perpendicular to this one, right? And I can just rotate like this and that plane. Bam. Okay, so we found the best fit. Hooray! Okay, and we call that second line PC2. Then we find a principal component 3 by finding the line that is perpendicular to both PC1 and PC2. And remember, in 3 dimensions, we can do that. And if we had more genes, we just keep finding more principal components by adding more perpendicular lines and rotating them till we found their best fit. This repetition helps give an intuition of how PCA can be applied to a data set with more than 3 rows. Anyway, you can also now see that each successful principal component gets smaller and smaller. PC1 has the longest line or axis. and PC3 has the shortest. The different lengths reflect how much variation in the data they represent. In this case, 94% of the variation in the data is captured by PC1 and PC2. Which means that if we wanted to, we could ignore PC3 and still have a graph that represented most of the variation in the original data. So if we wanted to reduce this three-dimensional graph to a more easy to look at two-dimensional graph, we can ignore PC3 and use the first two principal components to draw a two-dimensional graph, just like we did in the first example. So just like before, we project the data onto the principal components, and then onto PC2, and then we make PC1 horizontal and PC2 vertical, and draw the data points just like we did before. This is the real kicker, because this is the solution to the problem we spent so much time introducing at the start. Remember, the problem was that we had more data than we could graph. And we just showed how PCA can summarize that data and draw a normal two-dimensional graph from it by basically just focusing on the first two principal components and throwing everything else away. So that means it's time to say triple bam. Anyway, I believe that my StatQuest video on PCA illustrates trying to be a good helper, trying to be curious, and trying to be a clear communicator for a few reasons. One, it was created specifically to help my coworkers. I saw that they would need to understand these graphs, so I made this video. Two, I knew this might help my coworkers because I was curious about their work and I learned a lot about it. And three, I tried as hard as I could to communicate clearly by creating a relatively good introduction that introduces a problem that we want to see solved. I then show in a step-by-step way, instead of just telling, how that problem can be solved. Bam. They haven't given me the 5 or the 10-minute warning, so I'm just going to keep going with some more tips. You guys okay with that? Good. Got a thumbs up. Hooray. Okay, first, I want to point out how simple the graphics are. There's not a whole lot going on in this slide, and that makes it easy to focus on just the graph. So when you're making presentations, I'm a big fan of just like whatever you're talking about, just show that one thing. Don't show like 10 different slides or 10 different graphs and then say, oh, but we're only going to talk about this one thing, because people's eyes will wander. And they won't be paying attention to what you're talking about. So if you just have that one graph you're talking about, you say, we're going to talk about this one graph. They're going to look and they're going to see one graph, and that's the only graph they're going to look at. Also, the graph is relatively thick, easy to see lines and dots. And this makes the graph easy to see on small screens like cell phones. Second, I should mention that this video was made entirely on a laptop using a built-in microphone. I recorded this in the library, in fact. And I used the free software that came pre-installed with Keynote and iMovie to create the video. And you can upload a video to YouTube for free. So basically, it didn't cost me very much to create this video. And there was basically no risk, right? No one was going to come running after me with an axe for making it. I don't think, not yet. So if you're thinking about doing something like this, just do it. I want to encourage you, though, that if you are thinking about starting a YouTube channel, I highly recommend picking your audience. My audience was specifically my coworkers. So when I made my first video, in the first 12 months of it being up, I got 9 views. And that may sound like a small number, right, compared to the 3.4 million people that have watched this video. But 9 views was actually a huge success for me, because that meant my coworkers were watching it. And I got 2 subscribers, so that meant 2 of my coworkers thought that they liked it so much they wanted to see more. And so to me, that was a huge success, and it helped me focus on how I was communicating. And whenever I had a question, I was like, well, should I do it this way or that way? I'd go, I could even ask. I could say, hey, Dominic, my coworker, can you help me decide what do you think makes this clearer to you? That was helpful. Or I can just imagine Dominic. I usually, when I'm doing stuff on my own now, I just imagine Dominic in the background just looking bored or looking kind of like angry or just looking like, he's mad at me because he doesn't understand what the heck I'm talking about and I need to get my act together. Okay, lastly, I want to point out that I never once mentioned this equation in the entire video. That's the equation for singular value decomposition. Okay, this is because this equation is simply a compact notation of the ideas that I have described. Learning the ideas that this compact notation represents, however, turns out to be much more interesting and for most people, much more helpful than learning the compact notation itself. Without learning linear algebra and decoding this compact notation, people can now easily interpret PCA graphs, loading scores, and even eigenvectors. And they can tell you how the graph was drawn, all without having to decipher this equation. So I say bam. Hooray. This is the end? They still haven't given me the 5 or 10 minute warning. So get this, we're just gonna keep going. I've got more tips if you're interested in starting your own YouTube channel. You may not be, but if you are, I've got some tips on making slides. Personally, I like to use Keynote, but I started out using PowerPoint and that works just as good, so you just make slides however you wanna do it. Keynote has a fancy equation editor that makes mathematical symbols look nice, but whatever, who cares? Because the reason why nobody cares, or I don't care, is that I usually write the equations out as text because I think they're easier to read. And I can make them as big or as small as I want, and blocky and chunky, and I can color things easily. So I like to just write out the equations by hand. And I almost always draw graphs by hand because I need them to be easy to interpret on cell phone-sized screens. So I just drew that in Keynote, or I drew it in PowerPoint or whatever program I was using. Note, I focused your attention on the graph by covering the text and arrows with a semi-transparent white box. That's sort of a trick I use. I want you to be able to, I want that information to be there for reference. If you're like, well, wait a minute, what do those lines represent? It's there, but I really want you to be focusing on the lines. And so the lines are what stand out, and the reference material that's just there, just in case you forget what the lines represent, that's a little harder to see and you kind of have to search for it. Okay, the next thing I do is edit like crazy. Like that first draft is like your worst draft. You got to keep going. And it's hard to illustrate what editing looks like. Just know that a lot of what I do is editing. I edit like crazy. And usually I've been doing YouTube professionally full time now for about almost 6 years. I still go back to my old office and I still present my stuff for Dom and my old boss, and I get their feedback even today. I was just there a week ago. I still go back and I want to make sure that that I'm able to still communicate with the audience that I originally intended. So that's important. Okay. Blah, blah, blah. Oh. I also sometimes spend a lot of time on trying to create a dramatic arc. So obviously we talked about, we start with a problem, we learn how to solve the problem, and then we solve the problem. This is the format used by almost every movie you've ever seen. And I try to use that even in this mathematical setting, which is maybe a lot more dry and a lot more boring, but you can actually apply this framework to any presentation whatsoever. And I highly recommend using it because Hollywood makes billions and trillions, and so can you. Anyways, we're just going to go and say bam. Anyways, bam. Thank you guys very much. We have time for questions, I guess, because that's great. Anyways, thanks. Yeah. Yes, hold on. Let me get the mic to you.
So in scientific papers, you're supposed to, in the abstract, give away the answer, the solution at the beginning. What's your feeling about doing that in a presentation in a video?
Well, I kind of do in the video too, because the whole reason, so you set up this problem, and and basically once I set up the problem, I go, And now we're going to learn about the solution, principal component analysis. So I kind of give it away right then too, just like you would do it in an abstract. Yeah. You're close.
What made you what made you start with a YouTube channel instead of just showing the presentation to your coworkers?
Yeah, so the question was, well, why YouTube instead of just doing presentations? And get this, I started doing presentations. Every Friday morning I had this thing called Stat Chat. And I would invite everyone from the genetics department to come and listen to my Stat Chat. But this is an academic department. And that meant every 6 months people would show up and I'd have to repeat myself every 6 months. That's tedious, right? The other thing that's kind of annoying is if I teach lectures every Friday, that means I teach, maybe at the beginning of each semester, I teach R squared or t-test or something like that. I teach some concept. But whoever I taught may not actually need to know that concept for 6 months or even a year. So they spend a lot of time learning something and then they forget it. And then by the time they need to know it, they're like, oh, I think I remember going to something about this, but I don't remember the details anymore. So how much cooler is it to have a YouTube video so that when they need to learn it, they can learn it then? So it solved two problems. One is once I make a video, I never have to repeat myself. Two, people get to learn when they need to learn rather than when I have time to teach. And that's a big difference, right? Because when I have time to teach, it may not be convenient for them. So I saw YouTube as sort of like a tool that I could use to solve two of my own personal problems. One is I don't like repeating myself, and two, because it's boring, and two, people can learn when they need to learn. So when they're reading some manuscript late at night and they're like, and the R squared was, and they're like, what the heck is R squared? They can go and they can watch this real short video and they can learn about it, and then they can come back to their manuscript and keep reading. So that was the idea there. Any other questions? Yes.
Hi. So talking about the slide where you were saying you repeatedly edit your slides, when one of the problems I personally face when making slides is there are always trade-offs to any solution that you're trying to present or the problem that you're trying to solve for. How do you approach that when you're making your own slides? Because, hey, I've introduced a problem. Now there can be 5 different types of solutions depending on the conditions that you want to introduce to the problem. How do you approach that aspect of problem solving?
Yeah, that's a good question. The answer I have is I have a couple of things. One is I always try to make things as absolutely simple as possible, but still capture what the problem represents. So, for example, I have a video on how neural networks work. And I'd make the simplest neural network I could possibly make that justifies the neural network's existence. So instead of just fitting a straight line to something, because you can do that with linear regression, that's super easy, right? What I do is I have 3 data points, one here, and then one back down here. So we have to fit like a curve, like a bent shape to it. And then from there, I build everything out. But I try to make it as simple as possible. The other thing is, if there's lots of different things that I could talk about, and this thing could go for hours. So if people have watched my videos, you know that I say bam, and I say double bam, and then at the very end I go triple bam, right? And I've only done that once. I've only said quadruple bam once. And it sounds, as silly as this is, that's how I define how much content to put in a video, is if I've got more than 3 big, huge points, I've got too many. And what I need are more videos, or I need more presentations. I don't know if you've ever been to a presentation. I've been to many of these where people try to teach me too much stuff, and I'm great, I'm solid for about 20 minutes of that presentation, and then my brain is full. And then for the last 30 minutes, my head hurts, and all I want to do is leave because I can only learn so much. Learning is really hard, right? Your brain is like building new connections. You're doing all kinds of stuff in your head. It's exhausting. And if people try to teach too much, they'll get annoyed and frustrated and exhausted and just mad, grumpy. It's like getting hangry. At least that's how I respond to it. And so I try to restrict the amount of content I teach to just 3 main concepts in any go, and then I'll do a follow-up video or a follow-up seminar or something like that to pick up the pieces of the next part and then the next part. A good example, I've got a series of like 10 videos that describe logistic regression. That started off as 1. And I was like, I'm on like 50th BAM or something like that. And I was like, this is no good. I've got to split this up. So that's how I do that. I think they gave me like 4 hours to talk. I still haven't seen the 5 or 10 minute warning.
Because you said you had to break your videos up. So what is your timestamp? Are you shooting for 5 minutes, 12 minutes, 20 minutes?
Ooh, I would love if I could get everything down to 5 minutes. Because that was the original idea, was you're just like, oh, I want to learn something. And there's like 5 minute long video, and it's not a huge commitment of time. But the more I do this, the more I've discovered that I'm a 20-minute guy. And I just think everything I do takes 20 minutes, no matter what. So and that seems to be okay. I will say, though, that YouTube metrics suggest that most people are 6-minute people. So even though I make a 20-minute video, the first 6 minutes are really well watched, and then everything else is like, I'm kind of lost. So what does that mean? What does that tell me to do? That tells me to focus on the main ideas early and to fill in details and nitty-gritty things later. Also, so but I also think that's just important in general, right? If someone's presenting something to you, you want the most important stuff first. You don't want it to be last. You want it to, let's give me the goods. So that's it. Yes, we have someone in the back. Sorry.
Oh.
Yeah.
Hi. I just wanted to say I've been watching StatQuest for a while, and when I did my undergrad in statistics, it was super monumentally helpful for me. So like being able to see you do the BAMs live and all this stuff was really, really cool. So with that out of the way, I know that you also have a number of books about the things that you do, and I was wondering, like, what's the process translating the presentations from your videos into like books and publishing and translating and all of that?
Yeah. So yeah, I've got videos, but I also write books. Writing books is amazing, and I love it. The reason why I love it is the videos end up sort of being kind of rough drafts. In that I make a video about something, and I put it up, and I get a lot of comments, and a lot of people say, oh, I love it, this is great. But then a lot of people are like, at minute 7 and 32 seconds, I got confused. And I'll be like, oh, well, let me look at that. And I'll look at that, and I go, oh, yeah, I can see how that could be confusing. I can fix that. Unfortunately, YouTube itself doesn't let me do that. They're great for putting out cat videos, because you never need to revise or update or fix or improve a cat video. I mean, how could you fix a cat video? But for educational content, it's horrible, right? Because their whole algorithm is based on likes and engagements and views and things like that. And if I put up a brand new video that's got all lessons learned from the mistakes I made in that first video, and I correct everything so that I address everybody's questions early, and I fix it, nobody's going to watch that new video compared to the old one. And if I take that one down, I lose money. I mean, that's just the point. It puts me in a bind, and in that I've got a financial conflict of interest, because this is what I do for a living now, and I'm not making a great living, and so taking even a small economic hit is actually a big deal for me. And so what I love about the books is it allows me to finally address all those things that like frequently asked questions that I just know people are going to want. And the other thing I like about it is that they give me in YouTube, like I said, I'm a 20-minute person, and so I've got these 20-minute videos, but they're all kind of independent of each other, whereas the book allows me to have like a bigger narrative arc, and you can kind of see the big picture of how everything fits together. And so I really delight in writing the books. So that's that process. Yes, thank you. Yes, it's finally time for me to end. So thank you very much. I appreciate you very much, and have a great time here. Hooray.